Hello everyone and welcome back to my channel Gyan Sampada. Today we are going to continue with a quantum mechanical concept which is eigenvalues and eigenfunctions of J square and Jz. So already we have studied about the basic properties, applications of quantum mechanics, and even we have studied some of the details about angular momentum. And here J square is nothing but square of total angular momentum and Jz is the z component of total angular momentum. And under this, today we will be also studying some of the details about the ladder operators. So about ladder operators we have already studied a bit in our previous classes, which you can check out in the playlist section named Angular Momentum. So let's start with today's class. For that, we need to know some of the background, what we have actually studied. Under the heading of angular momentum, we have studied the operators corresponding to angular momentum, the commutation relations, etc. And while solving the commutation relations, we came to know that square of angular momentum, that is J square, is going to commute with the components of angular momentum, that is Jx, Jy and Jz. So their inner product equals to 0, which means J square is commuting with the components of angular momentum. In our previous classes, we made use of the symbol L, that is orbital angular momentum, and now we are using the symbol J, which is used for the general angular momentum. So this is the relation which we have already solved, but the components, that is Jx, Jy and Jz, are non-commuting among themselves. That is, if we consider the inner product of Lx with Ly, we saw that it equals to Ix cross Lz. Similarly, with respect to other components. In the same manner, Jx, Jy, Jz, their inner product is not equal to 0. So if we have the inner product of Jx with Jy, then we will have the value equal to Ih cross Jz. Therefore, J square and any one component of J, let us say Jz, can have the simultaneous eigenkets, that is eigenfunctions, at a time. And let us denote the simultaneous eigenkets by ket lambda m. So for time being, remember, lambda corresponds to the eigenvalue of J square and m corresponds to the eigenvalue of Jz. That's why we have denoted the eigenkets as ket of lambda m. So as now we have considered the eigenket, based on that we can derive other information from it. So let's look at the derivation part, where first we will consider the eigenvalue equation. One corresponding to J square and one will be corresponding to Jz. And for J square, we can say that the eigenvalue equation J square ket lambda m is equals to lambda into ket lambda m. We know what actually is eigenvalue equation. So whenever an operator, here it is J square, is operated on a function, here we have considered the function as ket lambda m. If it generates the same wave function with a constant, then such an equation is called as eigenvalue equation, and the wave function is called as eigenfunction, and lambda, here that is a constant, is called as eigenvalue. So we need to find out what actually this constant is going to be. And similarly, we can write the eigenvalue equation corresponding to Jz. So Jz into ket lambda m is equals to m into ket lambda m. So we can call it as equation number 1 and equation number 2, where J square and Jz are operators. Lambda is eigenvalue corresponding to operator J square. M is the eigenvalue corresponding to operator Jz, and ket lambda m is the eigenket or eigenfunction. We know that J square, that is the square of angular momentum, is nothing but sum of squares of its components. So J square can be written as Jx square plus Jy square plus Jz square. That's why we can rewrite equation number 1 something like this. So in place of j square, we have written it with respect to the components of angular momentum. And now we will separate it. And the separation is done in such a way that we are keeping jz square as a separate one, and here we are having the collection of jx square plus jy square into ket lambda m plus jz square ket lambda m is equals to RHS as it is. And now if we look at this equation, we have equation number 2, that is jz ket lambda m, that is equals to m ket lambda m. So we can substitute here and we can write in place of jz square its corresponding eigenvalue, that is m square. For jz it is having m, and for jz square we can write as m square. And to this equation we will multiply by bra function of lambda m from the left. So this notation is a bra function and this notation is a ket function. So throughout this above equation we will multiply from left side by bra lambda m. And if we look at the second term, we know that m square is a constant. So that can be brought outside the bracket notation. And similarly, lambda also can be brought outside the bracket notation as it is a constant. And first term we can write separately. So the above equation will be rewritten something like this. Bracket notation with jx square as the operator plus with respect to jy square is equals to lambda as it is. This plus m square will move on to right hand side and can be written as lambda minus m square into this function. And let us call it as equation number 3. Then already we have studied about the normalization and all. We have solved some of the problems where we found out the normalizing constant. So instead of integral form, we have just made use of bracket notation here. So this itself is nothing but the normalization condition, which in integral form can be written as integration of lambda m star into lambda m d tau is equals to 1. So whenever we are having a bra function, it is understood that it is a complex conjugate and the ket function remains as it is, which is evident in this integral form. So this lambda m itself is the eigenfunction what we have considered in equation number 1 and 2. So now if we substitute it back in equation number 3, we can write equation number 3 something like this, where the last part is going to be equal to 1, so that RHS will be just lambda minus m square. And we know that jx square and jy square, or in general we can say jx and jy, both are Hermitian operators, and we have studied the properties of Hermitian operator, and we know that their eigenvalues must be real. See, whenever we are having a real term, square of it is irrespective whether it is negative or positive, square will be positive itself. Both are squares, so totally positive with a sum is going to give a positive number. And this is equated to lambda minus m square. So RHS part also needs to be positive, that is lambda minus m square should be greater than or equal to 0. So if we bring that m square on RHS side, we can write lambda should be greater than or equal to m square, and let us call it as equation number 4. And now we will consider equation number 1 and operate it by j plus, that is raising operator from left side. But why that j plus is called as raising operator, we will study now. So when we operate it from left to equation number 1, which is the eigenvalue equation of j square, we get j plus into j square ket lambda m is equals to lambda j plus ket lambda m. So here you can write lambda first because it is a constant. Let us call it as equation number 5, and we already know that j square, that is square of angular momentum, commutes with j plus. So when both are commuting, inner product of j square with j plus is equals to 0 means AB minus B is equals to 0. J square j plus minus j square will be equal to 0. So we can write j square j plus is equals to j plus j square. So these two can be interchanged. And thus we can write equation 5 like j square j plus ket lambda m is equals to lambda j plus ket lambda m. And let's call it as equation number 6. And if we compare equation number 5 with equation number 1, then we can say that ket lambda m and j plus ket lambda m are the eigenkets of j square or eigenfunctions of j square with the same eigenvalue lambda. So here clearly we can observe that the constant, that is the eigenvalue, is lambda itself in both equation number 5 or 6 and 1. So the wave function associated with, that is the ket lambda m and j plus ket lambda m, both are going to act as the eigenkets itself. So we multiplied j plus from left hand side for equation number 1. Similarly, multiplying j plus on left to equation number 2, which is eigenvalue equation of jz. So when we do so, we get j plus jz ket lambda m is equals to m into j plus ket lambda m. And let us call it as equation number 7. If we look at it, we have already studied that the commutation relation of jz with j plus gives us h cross j plus. So both are not commuting to each other. And if we just expand it, we know jz, j plus inner product is jz into j plus minus j plus into jz is equals to RHS. We are having here j plus into jz. So we will rearrange this and that will be equal to jz j plus minus h cross j plus. So now we will substitute this equation number 8 in equation number 7. And after substituting, we will just separate it. So jz j plus ket lambda m minus h cross j plus ket lambda m is equals to m j plus ket lambda m. And in the same way, we will just bring this constant term on RHS side so that we get jz j plus ket lambda m is equals to m plus h cross into j plus ket lambda m. So let us call it as equation number 9. And just by looking at it, we can say that j plus ket lambda m is an eigenket of jz with eigenvalue m plus h cross and j square with same eigenvalue lambda. So what has happened here? When you have considered the j square commutation with j plus, we know both are commuting. So there is no change in the eigenvalue. But when we have considered z component of angular momentum with j plus, then we have observed that earlier it was m, eigenvalue was just m, but by operating we have got the eigenvalue as m plus h cross. So there is an increment of eigenvalue by an amount of h cross. And since the operator j plus generates a state with same magnitude of angular momentum, but with z component the magnitude is higher by h cross. And that's why j plus is called as raising operator. Raising means there is an increase. So clearly we observe that there is an increase in eigenvalue by an amount of h cross. This is how we can justify the name raising operator or how it is going to operate. So next question comes, what happens if we operate it repeatedly? So operating repeatedly by j plus, that is raising operator, increases the eigenvalues of jz in steps, and the steps will be of the amount h cross. And if it goes on, then what might happen? So this has to be stopped for the validity of equation number 4. If it goes on continuing, then our equation number 4, that is lambda should be greater than or equal to m square, that condition will not be valid. Our m square, which will be changing to m plus h, which on repetition we can say m plus nh, is going to become more than lambda, but that is not true. The main condition for the validity is lambda should be greater than or equal to m square. So there should be some limitation put over, and let us say the maximum value allowed for m for a given value of lambda without violating equation number 4 be mu. So then we can write the eigenvalue equation as Jz ket lambda mu is equals to mu into ket lambda mu, which we will call as equation number 10. So instead of m, we are having mu here, which will be the maximum limit of m, so that always m square remains less than lambda. So again in the similar manner, we will operate j plus from left side to give equation number 11, because when we do the operation from left hand side, again we know that commutation relation of Jz with j plus is h cross j plus. So when you elaborate it, what we have done in the previous slide, then we get Jz j plus ket lambda mu is equals to mu plus h cross j plus ket lambda mu. So earlier we just multiplied by j plus on left, and then we made use of the commutation relation. Then we have taken this h cross part onto the right hand side. Here it will be same as that of previous equations, only changes instead of m we are having mu. And since mu is the highest eigenvalue, mu plus h cross is not possible to be the eigenvalue, because we have considered maximum value which is allowed is mu. But here when you operate with raising operator, it is becoming mu plus h cross, which is not valid. And therefore we say that j plus ket lambda mu is equals to 0. And for this equation, if we multiply j minus from left hand side, again it is going to become equal to 0. And we know that j minus into j plus is equals to j square minus jz square minus h cross jz. And if we substitute this value in equation number 13, we get this equation, and further substituting the eigenvalues. So for j square we have lambda, for jz square we have mu square minus h cross, for jz we have mu, which is the maximum value of m. So after substituting we get this equation, and clearly we know that ket lambda mu cannot be equal to 0, because itself is a eigenfunction. If there is no eigenfunction or eigenket, then we won't have a particle as such, because any wave function is going to give us detail about presence of a particle. If wave function doesn't exist, then what is the meaning of doing all these things? So we say ket lambda mu is not equal to 0, and this equation has to be valid, means the first part, that is lambda minus mu square minus h cross mu should be equal to 0. So when we rearrange, we can say that lambda is equals to mu into mu plus h cross, and we will call it as equation number 14. So till now we studied about the background, and we have started deriving the eigenvalues and eigenfunctions of j square and jz, where we came across the raising operator. When we use the operator j plus, what happens to the eigenvalue, due to which it is called as raising operator. And in our next class, which will be the continuation of this class, there we will be studying about the lowering operator, how it is going to work, and finally we will give a conclusion where we will get a complete picture about eigenvalues and eigenfunctions of j square and jz. So till then, stay tuned. See you in our next class where we will complete this concept. So study well, work hard, and thank you for watching.